many of you know, I come from a bit of a life sciences background, so I ran into this idea called genetic algorithms, and I'd like to share what they're about with you. So let's dive right into it. What is a genetic algorithm? It sounds like a pretty complicated thing, but it's really not so bad, and hopefully by the end of this presentation, I'll have demystified it for you guys a little bit, and maybe you'll even feel confident enough to try rolling your own. But the essence of it is that it's an optimization strategy that mimics natural selection. So basically, our algorithms will be generating solutions to problems and kind of apply this principle of survival of the fittest to them. And so how do we make one? We need a few things first, namely a problem to solve. Depending on the kind of problem, we'll have to tailor our algorithm a little bit, but the overall steps are usually about the same. We're also going to need a fitness function. And what I mean by that is that we need a way to grade solutions, right? What makes a good solution? What makes a bad solution for our problem? And then finally, we need a way to represent these as DNA. This probably seems a bit vague to you guys, and it's probably unclear how this goes into code. So we're going to walk through an example. I think most of us have at least heard of the Traveling Salesperson Problem. Essentially, the gist is given a set of cities, what is the shortest path that connects all of them, with the condition that your first city is also your last city, right? So it's a round trip. And I guess it's kind of appropriate that I'm doing this on our week 1 of Reacto and talking about algorithmic complexity. So you might imagine a naive solution to this would be to take all of our cities and actually generate every single possible permutation of routes between them. And that takes a really long time. It takes factorial time, which, as we know, with inputs even as small as 20 or 30 cities, begins to take an unmanageably long amount of time. So we're going to see if we could do a little bit better with our genetic algorithm. And so first, we're going to represent our routes as DNA with an ordered collection of cities. In my implementation, I ended up using an array. And basically, the 0 index is the first city, the 1 index is the second city, and so on and so forth. And then also, again, pretty straightforward what our fitness function is, right? The shorter the path, the better. Basically, you would just go through a route, city to city, sum up all the distances, and then kind of rank them. So let's go a bit more into detail. Step 1 for our algorithm, we'll have to generate a seed population, kind of like a generation 0. And so say here we have cities 1 through 5, and we want to find the shortest route between them. Here I've just kind of randomly shuffled the cities 3 times, totally random, and then placed them in our starter generation. Then I'm going to rank the fitness of each of these routes. And so again, the shorter the distance, the higher the fitness. And then after that, we're going to randomly select 2 of these routes. I say randomly, and there's definitely an element of randomness to it, but usually the selection algorithm actually is biased towards the fitter ones. So the fitter you are, the higher chance you have of actually getting picked. And then, so this algorithm is modeled after biology, and so once our algorithm kind of acts as matchmaker for these 2 routes. Maybe they go on a few dates and such, and they really hit it off. And we hit step 3, mate. So here we have our 2 parent routes, route 1 and route 2. And here's how we're going to make a child. First, we take a random segment of random length from one of the parents, transplant it directly into the child. Notice how the index is the same as it was in the parent. And then from our second parent, we're going to fill in the rest of the genes. So we start at city 3, the index after the end of the segment. Fill that in. City 5 is already in here, so we're going to skip over it. City 1 also is already in here. City 2, City 4, and then bam, we already have our first child for our algorithm. And then after that, we're also going to apply a mutation step. So essentially, we're going to iterate across this collection of cities, and using a predetermined probability, we're going to decide if a city is going to mutate or not. In this case, let's say City 1 has been selected to mutate. And because for our traveling salesman problem, we have this constraint where all routes should have the same cities and cities should only appear once, the mutation step is just a simple swap, right? So here we swap city 1 and city 2, right? And that's about it to create a child. We place it in the next generation and rinse and repeat until we have a new generation that was the same size as the old one. And hopefully, if we've constructed our algorithm right, over time, we're hoping that our algorithm will generate fitter and fitter generations. So let's take a look at what this looks like in practice. So I've coded up a quick demo. Please excuse the awful front end. Anyway, I'm just going to get this going, and let's orient ourselves. So over here on the left, I am displaying the fittest individual of the current generation. And then up here, we are displaying the fittest individual that we have generated so far. Oh, and actually I forgot to mention, so here we're only displaying one, but this is one of 50 others. And so we kind of have like 49 unsung heroes here who are helping to contribute their genes to the next generation. And here, this is just a really coarse graph of the fitness of these individuals, so we get a feel for how things change over time. Right, so yeah, the steps we just went over in the slide, that's one generation, right? So we just do this over and over and over again until we arrive at a solution we're pleased with. So now take a look at these parameters down here. We have population size, which is basically just the size of each generation. We also have the crossover chance. What I mean by this is we don't always cross over to create children. Every now and then, we'll actually just take a parent and clone it down directly, kind of to have a stronger way of preserving the genes. And then we also have our mutation chance, which kind of self-explanatory again. It's the chance that cities will swap within a root. And so let's see how each of these kind of affect our algorithm. So I'm going to start with a pretty small population of 15. I'm going to get rid of mutation for now. It kind of gets in the way of the demo because this is all probability-based. But anyway, we'll see that if we try to run this, oops, I should also do the step size. If we try to run this, it actually gets stuck here. And I'll try and run this over and over again, but we'll see our algorithm continuously get stuck on pretty poor solutions. And basically, the problem here is that we have low genetic diversity. Because our population of solutions is so small, over time, they really start to just look more and more like each other, and they're kind of unable to break out of that local optimal solution. So we can try to mitigate that by increasing our population size. And oh, we actually have a pretty decent solver now. This won't always get the best solution, and sometimes it'll take a while. But it's a great deal better than having only 15 routes in our population. So diversity is probably a good thing. Who knew? And then from here, let's take a look at, I'm actually going to skip over crossover for the sake of time, but let's take a look at how mutation plays into this. So let's go back to our small population of 15. Right, we were getting stuck before. And so if I introduce a little bit of mutation, about 5%, we can see that we actually don't arrive at this problem anymore of getting stuck. We don't exactly converge on a great solution very quickly either. But mutation really helps us to explore more of the solution space and kind of continuing to try to find a good solution. And then we'll see how this affects a large population size as well. Namely, it'll make convergence to a solution pretty difficult, just because we're basically adding statistical noise with this mutation chance. And so this solution won't converge quite as quickly, but it probably has a good chance of arriving at a good solution relatively quickly, and it might even find the best solution given enough time. Right, and so back to the slides for a little bit. What I've kind of demonstrated just now is referred to as the local optimum problem, this trade-off between exploitation and exploration. And that's not really a trade-off unique to this kind of algorithm either. It's a trade-off that exists for really anything, including human beings or other living organisms that can learn or adapt to solve their problems. The essence of it is, do I keep doing what I'm doing, maybe with a few small changes and try to get really good at that? Or do I try something new? Do I try and explore my options, maybe try a new paradigm? And so earlier when we were getting stuck on our solutions, we were essentially hitting local optima in the global solution space. And the hope is that by introducing decent crossover and mutation, we can not get stuck, maybe even climb down or jump across these little local optima in our solution space. And so, a final note, as you saw already, we don't always hit the optimal solution this way, but yeah, this is a heuristic approach, but we do usually get a pretty good one pretty quickly. Right, so remember, these are time complexities for, or how long operations take at given time complexities, and with enough cities, this kind of operation could take years and years with a brute force solution. But I'm gonna show you right here. I took a screenshot of my algorithm trying to solve a 30 random city problem. And if you look right here in the best solution it generated, it's definitely not the best solution possible, but it's really not bad. It's actually probably quite close to what the optimum would be. And rather than taking years and years to get to here, this took about 30 seconds on my several-year-old MacBook Air. And so hopefully I've helped demonstrate what genetic algorithms are. And yeah, actually, so I did skip over a bunch of implementation details. And I'd be happy to Slack out code later or something so you could kind of see how you might want to implement one of these in actual just plain JavaScript. But yeah, that's it. Thanks for listening.